In this last slideshow about research methods, I'm going to go through some of the structure of the living brain and some of the assumptions that we make from correlations. In this section I have called correlating brain activity with behavior. If you notice in the original outline, when I have the outline up, it's called the structure of the living human brain. I'm talking about the same thing here, right? So when we're looking at the structure of a living human brain and we're asking, what can this person do? What can they not do? What is their behavior? What is their personality? Maybe we are asking what is the correlation between that brain anatomy with their behavior. And this really all started back in the early 1800s with phrenology. It was actually a couple hundred years before that, maybe almost 200 years before that, when it was first proposed that potentially different functions of the brain were, different functions were occurring in different regions of the brain. But for a long time, there weren't a lot of proponents of that theory. Obviously, that's what we know occurs now. And by the 1800s, the scientists were starting to accept that, and phrenology came about. I have seen several really neat phrenological maps and models in people's offices, where what they would do, and what this is showing with these numbers on the brain, is that they would feel the bumps and protrusions at the skull, and then make some assumption about brain activity, or what that means as far as your personality, behavior, your ability with language, all of those things. Of course, we now know that phrenology is not an answer to how to look at brain activity, that at the level of the skull, that's not showing us what's happening just feeling the skull with your fingers. That's not going to tell us what's happening in the brain. But this was around for a while, was considered scientific for a while, and then eventually it started going into more like carnival shows and so forth, as it lost more and more credibility over time. I keep thinking of one more thing I want to say after I've left a slide, but I used to sit in on a psychophysiology training grant talk every Monday for years. And Manny Donchin, if you get a chance to read anything by him, he was kind of one of the founders of a lot of some of this field. He was back when they were doing a lot of PET studies. And when I was in graduate school, the fMRI was becoming more common. It wasn't like it is now, but it was becoming more common. And so Illinois had an fMRI machine, and we're doing studies on the fMRI. And he would, sometimes in that training grant talk meeting, he would talk about how we're the phrenologists of our time, that we are still making guesses, and we are still looking at correlations and making assumptions from those correlations. And we really still need the cognitive, or if I'm looking at something about cognition, I need to look at the tasks and the behavior as well as the brain anatomy, and I need to realize that I am making some assumptions there. But anyway, so we've moved on from phrenology, and for a while we used, and we still use, for people especially who cannot go in an MRI machine, if we're looking at, if we have a patient and we want to look at brain activity or brain structure, a lot of people have a pacemaker or some kind of piercing that's in a spot where something, or metal in their body somehow, so that they cannot go in an MRI. So we still do use PET for certain things. We still do use this CT scans. So computerized axial tomography, we're looking at structure, and this is basically getting X-rays, but from many different angles. So they have an X-ray beam, an X-ray detector, and they rotate. For us, because we're looking at the brain, they rotate around the head, taking X-rays from many angles. And so then they assemble this series of those successive slices that are happening over time as they're moving those machines to construct images of the entire brain, and it lets us look at the structure of the brain. This is the least expensive and most widely used method for looking at brain structure. Okay, so here is, I'm showing you some CAT scans of a woman with left hemineglect. Okay, so you have to kind of imagine, let's see if I can do this right. My left and rights, because of my bit of cerebellar problems, are difficult for me. On the picture, right is to your left of the person. So you kind of have to imagine spinning your head around and starting and then starting down. You can see the sockets of the eyes, and then in one, and then moving up right through the brain, and things look pretty normal. As we move into, I'm going to go ahead and move to 4. You can start to see on the right hand side of the person, our left hand side, this little white space there towards in the parietal lobes. Remember, we talked about left hemineglect being that right parietal lobe damage that causes an inability to really pay attention to the left side of space or the left side of the body and so forth. And then we're moving up, so we see that little tiny white space, which is the damaged brain, and then we move up the next successive slice, and you can really see in number 5 that area that is damaged in the parietal lobes. And so that gives the CAT scan gives us a pretty good idea of where there is brain damage or where there's a tumor and so forth, about brain structure. Okay, so we're finally to magnetic resonance imaging, which most of us have had some experience with. If you haven't had an MRI yourself, you know somebody, most likely, who has had an MRI. And this is how they're looking at the structure of whatever. Sometimes someone's getting their leg looked at, or their something in their abdomen or whatever. But we're going to look at the brain, of course, because we're talking about the brain. When we're in the magnetic resonance imager, we have this magnetic field. We're using those radio waves and the computerized enhancement to interpret that information and give us an idea of the structure. And what's happening in that magnet, so atoms with odd numbered atomic weights have a certain axis of rotation, and so different structures in our body have different amounts of water. And the MRI applies this powerful magnetic field to align all the axes of rotation of those atoms. And then they pass this radio frequency field. They pass it through, and then it stops. They start it and then it stops. And that radio frequency field tilts those atoms. And then when it's turned off, those atoms, those atomic nuclei, relax, and they return to their original axes, releasing electromagnetic energy. So the MRI then measures that energy that's being emitted and tells us about the different structures. Tells us about the different the different structures because of the different amounts of odd numbered atoms, or different amounts of water really in those structures. So the MRI provides much better imaging of brain structures than CAT scans, and we get these 3-dimensional images of the brain with remarkably high resolution. And you can see a scientist there looking at an MRI. It's a little bit smaller than I'd like, but you can see just how the spatial resolution on those brain structures. You can look at anatomical details smaller than 1 millimeter in diameter. This is a nice summary slide, I think, in a way, and you can pause this or go back to your PowerPoints and say, I like this table. A lot of people like tables to learn from, and this comes from the Laura Freeberg's Discovering Behavioral Neuroscience that I have taught from one semester. But she goes in a very similar order that we do, that Cal does, and that we did this semester, of starting with the brain damage, people who have strokes, then the ablation and lesioning, the taking the animals and giving them some specific area where we do some damage. She has the gene knockout. We can do various things with animals as far as knocking out particular genes or making them so that they're not active. Also, taking particular gene, making or basically giving an animal a gene or a receptor site that is active, that is normally not active in that animal. So that's something we skipped, and you don't have to really know. But then the transcranial magnetic stimulation, we did talk about that as well as a temporary lesioning. But then we went into the stimulating of the brain, and she goes into that as well for a couple. So this is a nice summary slide. And then going from stimulating to recording brain activity, various ways of recording brain activity, if you want to go through those, and then correlating brain anatomy, or what we see of the structures of people's brains, or what might be clearly damaged or not damaged, and then seeing what is damaged or impaired as far as behavioral outcomes from the CT and MRI scans. So this is a nice summary slide, and we will get back together on Monday. And if you're looking through this and have any questions or whatever, you have any questions anywhere, but this is a nice place to see, do I have questions about the research methods in general?